This conference will now be recorded.
Hello everyone, we'll start with the problem. Last day we ended with oxidation state, and based on, not oxidation state, that is oxides of group 14 elements. Based on this, we'll discuss this problem, and after that we'll discuss halides of group 14 elements and the different allotropic forms of group 14 elements. Okay. So this problem, as we can see, it is related to the oxides, right? It is saying that a group 14 element is oxidized to form corresponding oxide. So suppose the element is E, because we do not know which element it is. We are oxidizing it and we are getting the corresponding oxide. Now we know there are two types of oxide. It may be type EO or it may be type EO2. Okay. So we are getting an oxide. Now this oxide is gaseous in nature, that is mentioned clearly. So this is the first information. This is gaseous. The second information is when dissolved in water, pH of the water decreases. So we are dissolving it in water, and what is happening? pH is decreasing. Now pH decreasing means the oxide is producing some acidic solution. Okay. So these are the informations that are given. Some more informations are there. So I'm just numbering it. This is number one information. It is gaseous in nature. The second information is when we are dissolving it in water, pH is decreasing. And the third information, further addition of group 2 hydroxide. Now group 2 hydroxide means, remember, alkaline earth metals. Group 2 means magnesium, beryllium, calcium. So just take any hydroxide. I'm taking here calcium hydroxide. So when we are adding calcium hydroxide to this solution of, that is the aqueous solution of this water, of this oxide, then there is precipitation occurring. So total three informations are there, based on which we have to answer. Now look at the options. Here we have the type EO2 oxide, which is this one. This is EO2 type, EO2 type. This is also EO2. This one is EO type. But important point is it is gas, and we know CO and CO2 both are gas, but GeO2 and SnO2, these two are not gas. So based on this, we can cancel A, we can cancel D. Now out of CO and CO2, which one decreases the pH when dissolved in water? Now CO, its water solubility is not very good, but if we consider CO2, in water it produces H2CO3 acid, which is carbonic acid. That means now we can understand how pH is decreasing, because acidic solution is produced. So it must be CO2. And what about the third information? The third information is saying further addition of group 2. So when you add CaOH whole 2, that is calcium hydroxide, in H2CO3, then this carbonate will replace this hydroxide and we will get CaCO3. It may be MgCO3 also. But all these carbonates, because of their poor solubility, there will be precipitation. Okay. So carbonate anion is basically replacing this hydroxide anion of group 2 hydroxide. So CO2, it will form carbonic acid in water. So that is why pH is decreasing. CO is neutral. That means even if somehow you are dissolving in water, there will be no acidic solution formation. And these two are solid. So we can cancel A and D. So CO2 will be the correct option. Carbon dioxide. Fine. Now we will start halides of group 14 elements. Oxides we have seen in the last class. Now we will see the halides. Just like oxides, remember two types we have seen. One is EO type, another one is EO2. Now here also, because of two different types of oxidation state, when it will show +2 oxidation state, then the type will be EX2. When it will have +4 oxidation state, now the type will be EX4. Two types there. Now the thermal, first we will consider the EX4 type. Look at this order. This is the order of thermal stability of group 14 tetrahalides. So this one is tetrahalide, this one is dihalide. Tetra, because it is 2 and 4. So this is the order of stability. So maximum stability we can expect for CX4, and then gradually it is decreasing. So the size, when we are moving down the group, the size is increasing. Sorry, it is X. So consider all of this as X. It is not just true for Cl. You can write it for Cl, but as it is mentioned for tetrahalide, so we will consider the general one, not specifically tetrachloride. So this is the general way we can express the order. And as we are moving down the group, the size is increasing, the bond distance between the element and the halogen is high, so bond can be easily broken. So thermal stability is decreasing down the group. Now most of these EX4 or MX4, whatever you say, where M is the element, they are covalent in nature. And as there is total 4 coordination, it is tetrahedral and the hybridization is sp3. Just take any example. Suppose I am taking the example of CCl4. So it is sp3 hybridized and tetrahedral. Now, though we are saying that all of these are covalent, there is 2 exceptions. That is for the last 2 elements, TEEN and Pb. When TEEN and Pb, they are with fluoride anion, then there is some ionic nature. Fine. So for these two, it is not covalent nature, it is ionic in nature. Now, thermal stability, when you have fixed the halogen, suppose the halogen is you have fixed to Cl or you have fixed it to Br, then this is the order. But suppose you have fixed the element and you are changing the halogen. So when there is increase in size of halogen, so what I am trying to say, suppose you have fixed it to E, any particular element. So what about the stability of ECl4, then EBr4, and then EI4? So what we are doing, we have fixed the element, but we are changing the halogen. With increase in the size of halogen, thermal stability is again decreasing, which is clear from this example. If you consider lead, that is, suppose E is equal to lead, then ECl4 means PbCl4. This is stable. Now go to the next halogen, which is Br, PbBr4, it is unstable, and C, PbI4, it is not known. So what it proves, that when you are changing the halogen, you are increasing the size gradually, keeping the element fixed, then decrease, there will be decrease in thermal stability. Okay. Then CX4. CX4 means it may be CCl4, it may be CBr4, like this. We will take this example, CCl4. It cannot be hydrolyzed. Now why it is so? Because it cannot expand coordination number beyond 4 due to non-availability of d orbitals. So that is the reason when it is reacting with water, there is no reaction. Actually, if you make the condition very drastic, very high temperature, maximum you can get a different type of compound, which is COCl2. But it is not hydrolysis product. It is as if some Cl is replaced by water. Though water is not exactly present, what happens? Suppose 4 fluorine atoms are there. If 2 of them replaced by OH, but remember, it is not very easy reaction. It will be only if the condition is very drastic. But this is not hydrolysis product. Now, these 2 OH, if this OH bond is broken and there is CO double bond and this OH is completely removed, now it will form compound like this. So it is carbonyl chloride, COCl2, but this is not hydrolysis product. But if you take the next elements halide, which is SiCl4. Now it can react with water and it can form SiOH4. Now one question may arise that, as it is mentioned, that is the explanation is mentioned that it cannot expand coordination number beyond 4. but in the final product the coordination number is still 4, right? Then why this fact is so important, that in carbon there is no d orbital, so we cannot get COH whole 4 type of product. Basically, if you compare these two reactions, we are not getting any of this type of product, COH whole 4, but we are getting SiOH whole 4. But both are 4 coordination. Then how the question arises that non-availability of d orbital is actually the reason why hydrolysis of CCl4 is not possible. So what happens, if we want to know the answer of this question, basically we have to go into the details of the mechanism. If you look at this simple step, it is not detailed mechanism. Here what is happening, simply this Cl is replaced by OH, that is all the Cl replaced by OH. But if you go into the details of mechanism, what happens when the water molecule attacks, I'm writing water in this way, it attacks here. So it is not that suddenly the SiCl bond is broken. So what happens when the first water molecule is attacking the silicon, there is a penta coordination type of mechanism. That means in the intermediate, or even if you consider transition state, there is more than 4 coordination, and more than 4 coordination is possible only if there is d orbital, availability of d orbital required for that type of mechanism, where simultaneously 5 bonds are present in the Si. Though in the final product you will get only 4 bonds, 4 coordination is again reached, but in the intermediate there is more than 4 coordination. So that is why d orbital availability required. But this type of mechanism is not possible with CCl4 because there is no d orbital. But if you make the condition very drastic, maximum you can get this type of carbonyl chloride product, but that is not the hydrolysis product. Okay. Now this is very important information. You can get problem based on this. Come to the other halides. Next we have the stannic chloride. Stannic chloride is SnCl4. When you are boiling it in water, it yields metastannic acid, which is H2SnO3 and HCl. But directly you do not get this product. What happens? First there is formation of SnOH whole 4, as you can see here. And the equation is just the same equation as you have seen in the previous slide. Just in case of Si, now we have Sn, that is TeenCl4, 4 water, and SnOH whole 4. Now this is silicic acid. Silicic acid is this one, SnOH whole 4. Now if I write SnOH whole 4 like this, now what will happen? One of the OH, if this OH bond I am breaking and another OH is removed like this, then we are left with this type of structure, which is nothing but H2SnO3, same structure, right? So in this way we can explain how we are getting metastannic acid. It is not directly that we are getting this compound. First there is formation of SnOH whole 4, and then we are getting, because of loss of water molecule, we are getting H2SnO3. Now we will see the dihalides, information related to dihalides. The stability of dihalides increases steadily as we are moving down the group, and that is because of inert pair effect. Now when I'm saying dihalides, now the oxidation state is +2. In general, if I write EX2, here oxidation state is +2, right? Now we know that +2 state, group 14, as we move down the group, because of inert pair effect, the tendency of +2 oxidation state compared to +4 is more. So that is why here PbX2, so you can see double arrows are there. It is not just greater, it is very, very greater. So GeX2, it will not be very stable. That is GeCl2 or GeBr2, it will not be very stable. And compared to that SnX2, it is also much, much stable, and lead is maximum stable. And in this order, you will not find CX2 or SiX2, because for these two elements, the first two elements, dihalides are not so important. Dihalides are, that is plus 2 oxidation state is important down the group. For carbon and silicon, it is mostly plus 2. So that is why in this order only 3 elements are mentioned: germanium, tin, lead. Considering thermal and chemical stability, not just thermal, also chemical stability if we consider, then GeX4 is more stable than GeX2. Now GeX4 is more stable than GeX2. So here the only difference is in the oxidation state. Here it is plus 4, here it is plus 2. That means Ge in plus 4 state will be more stable compared to plus 2. But when you consider PbX4, now it is reverse. PbX2 is more stable compared to Pb2 plus. Okay. So this is important information. And carbon and silicon, there is no dihalides. Even if you see dihalides, that will be very, very unstable. These dihalides are sp2 hybridized and have a bent shape. So just take the example of SnCl2. It will have bent shape like this, and there is a lone pair. Now how I will explain this? It is sp2 hybridized. So for tin, if you consider Ns, so 2 electrons are there, and Np2, right? Now after sp2 hybridization, there will be total 3 sp2. Now out of these 3 sp2, in one sp2 there will be lone pair, and total electron is obviously 4. So these two will be used for bond formation with chlorine, and this is actually the lone pair. So total 3 coordination, and it is bent shape, because if you just omit the lone pair, rest of the parties, it is this type of shape. So that is why it is bent shape. Otherwise, if you consider this, that is sp2 and 3 have total 3 coordination, then it is trigonal planar, but without the lone pair, it will be bent shape. Which of the following is not correct? So in this question, we have hydroxide, we have halide, we have oxide, and there is also bond energy related information. Okay, which of these not correct? So we have to find the false one. GOH2 is amphoteric. Now this is correct, but even if you have doubt, just go to the next one. The next one is saying that GeCl2 is more stable than GeCl4, but that is not true. We have just seen that GeCl4 is more stable than GeCl2. So plus 4 state is more stable. This is the reason. So this statement, this is more stable. That is not possible. This is true for lead, not for Ge. So suppose why I have just said that if you have any doubt in any of these options, suppose GOH2, whether it is amphoteric or not, if you are not sure about it, but as we know that the second one, GeCl2 is more stable than GeCl4, this is obviously not correct. So the other one has to be correct. So this is true, this is false. Then GO2, we have already seen in the last class, it is weakly acidic, and it reacts with NaOH. So we can see the reaction. GO2 when reacts with NaOH, it forms sodium germanate, Na2. So this reaction I have already shown in the previous slide. I'm just again writing it. So it is reacting with base, so it is weakly acidic. It is true. And as we know, when we move down the group, the bond distance, that is the EE bond distance, whether it is CC or SiSi or GG, it decreases. So this table is already shown. CC, see, 348, then gradually it is decreasing. So it is 260, it is 240. So it is lesser than that of SiSi. It is 297. So down the group, decrease, bond energy decreases. Okay. So this is the correct option because it is the wrong statement. This question is related to halide, and only SnCl2 is present here. SnCl2 acts as reducing agent. We have to find the reason. Now SnCl2, here oxidation state is +2. Now it is acting as reducing agent. It means what? It means Sn2 plus, it is giving electron and itself is oxidized. If I write this equation, then only proves that it will be reducing agent, because reducing agent, it has to give some electron to some other species, right? Now come to the reason. SnCl2 can accept electron readily. Now what it means? That Sn2 plus accept electron readily, then it will be converted to Sn. But that doesn't mean that it is reducing agent. It means it is oxidizing agent. It is accepting electrons. It is obviously not correct. No question about it. Then Sn2 plus is more stable than Sn4 plus. So it is saying Sn2 plus is more stable than Sn4 plus. So if it is true, then why it will give 2 electron to some other species so that it can act as reducing agent? It is possible only when Sn4 plus is more stable, right, than Sn2 plus. So the second statement, that Sn2 plus less stable than Sn4 plus, just reverse. That should be the correct option. That is why there will be a tendency for Sn2 plus to be converted to Sn4 plus, because it is more stable. So this must be logically correct. Okay. And the last one is saying that Sn2 plus can be easily converted to metallic tin. Now this is again saying that it is accepting electron, then it is converted to Sn. That is the meaning of this sentence. It is converted to metallic tin. Metallic form means zero oxidation state. So this is also not correct. Now C is correct, fine. But if we go into the details, that why, because we know that G for germanium, G4 plus is more stable, that we have just seen in the previous problem. But Sn is coming after G and then lead. And for lead we know 2 plus is more stable because of inert paired effect. But why the inert paired effect is not so effective for tin? Actually for tin there is another explanation we can give. Inert paired effect is maximum for lead. But for tin, why it is so poor? So here some other explanation is there. The other explanation is the reduction potential for Sn4 plus Sn2 plus system is 0.15 volt. Now from this value you will have some idea whether a system will be, that is this type of system. We know we represent any reduced state, oxidized state in this way. Always we write the oxidized state first, then there is a oblique sign, then there is the reduced state written. So for any of these system, when this reduction potential value is very highly positive, then that means that the tendency to accept electron and to be converted to the reduced state, that tendency is very high. But if the value is going towards negative, or it is going towards zero, see, it is very low value. It is not negative, that is fine, but it is very low value. So when it is going towards negative or going towards zero, that means the tendency to give electron to other species and itself oxidized, that tendency is high. Just you know that Mn, we know that manganese, when it is in +7 state, it is very oxidizing in nature. So for Mn, from +7 state to +2 state, that is, it is reduced. For that system, reduction potential value is around 1.51 volt. That means it is very high value. And see here it is 0.15. That means it is very low. So why I am giving the manganese example, so that you can compare. So manganese is very 7 plus and 2 plus system, if we consider, that is very oxidizing. That means there is a tendency to accept electron and to be converted to Mn2 plus. So there is reduction potential value for that system is 1.51 around. But here it is 0.15. That means the tendency that Sn2 plus, it will give electron and itself be converted to Sn4 plus, this tendency is very high, which is clear from this value. So considering all this, we can say that Sn4 plus is more stable. Its reduction potential value is also indicating that. And here inert paired effect, that is with inert paired effect, we cannot give the explanation. Fine. So Sn2 plus in 2 plus state, there is a tendency to act as reducing agent. Okay. Here we have all are group 14 elements, obviously carbon, silicon, germanium, and we have two types of halogen. Chloride is there, and for the last option there is bromide also. We have to find the least thermally stable one. First, what you will do, just forget about Br, because only in these three the halogen is same. So when you are comparing, at least one part you have to fix, either fix the central atom or fix the halogen. So here we have fixed the halogen, and now you are moving from carbon to silicon to germanium, and we know when we move down, keeping the halogen fixed, there is decrease in thermal stability. So CCl4 maximum stable, then SiCl4, then GeCl4. Now you can compare these two. When you have fixed the central element, G is the central element, you are changing the halogen. Now when the halogen size is increased, stability is decreased. So considering all these, GBr4 should be the least stable. So see, thermal stability of tetrahalides, we know this is the order, there is smooth decrease down the group. And in terms of same metal with different halides, better we say element, not metal, because all these elements are not metals. So with same element but different halides, now the order is like this. So considering all this, GBr4 should be the least thermally stable species. What is the product of SnCl4 hydrolysis? Remember what we have seen in the table of in the slide of halides. SnCl4 when reacts with water, basically 4 water. First there is formation of SnOH4. Then there is removal of 1 water molecule. And after all, there is formation of this species, metastannic acid, SaH2SNO3. Just have a look in that slide. I'm talking about this one, H2SNO3, metastannic acid. Sorry, it is not. It is SNOH4, okay? Silicic acid is SiOH4, not SNOH4. So in this case, what we are seeing, when SNOH4, you are from this molecule, you are removing 1 water molecule, then there is formation of H2SNO3. There are total 4 options, and this will be the correct option. H2SNO3. Okay. Next question here we have, which of the following occurs as a consequence of inert pair effect? Now here we have total A, B, C, D, E. Total 5 statements, right? And we have to, options are 4, and it is in the first option ADE, then DE, then all these statements and ABC. So which of the following occurs as because of inert pair effect? So it is not that we have to choose which one is true, which one is false. It may be true, but the reason for the statement should be the consequence of inert pair effect. Okay. The first one is saying that SnCl2, that means Sn in 2+ state, it is acting as reducing agent. That means it is giving 2 electron and itself is converted to 4+ system. Now it is true that it is reducing agent. We have just discussed that because reduction potential value is very low. So the reason behind it is not inert pair effect, because when we are talking about inert pair effect, then in general, if I write the element for group 15 as E, then it will always have a tendency to move from E4+ state to E2+ state, because only in 2+ state these NS electrons, they remain in paired state. Only the electrons in NP that will take part in reaction. But when it is E4+, now this pair is broken and you have 4 unpaired electron. Okay, so inert pair effect means this situation where this pair is inert and E2 plus state is more stable, but here it is moving to SN4 plus, so it is not the consequence of inert pair effect. A should not be present in the options, and if it is so, see, A is present in option 1, in option 3, in option 4, so these 3 should not be correct. So in this way also we can choose that option 2 is correct, but here we will also see why the other options, how we can reject or accept, that is why D and E correct, that you have to see. Next statement is saying that SnCl4 acts as oxidizing agent. It means what? SnCl4 means it is in 4 plus state, and if it is acting as oxidizing agent, that means it is accepting electron and it is converted to 2 plus, or it further there is some more oxidation, that is it is itself is acting as oxidizing agent, that means it is accepting electron. So if there is further acceptance of electron, it can convert to Sn. But this tendency is not present. This is the reverse tendency that is present, this one. So this is not correct. Then SnO2 is amphoteric in nature. Okay. So SnO2 is amphoteric in nature. That means it can react with both acid as well as bases. That also we have seen in the oxide in the slide where oxides are discussed in the previous class probably. But it is not related to inert pair effect. It is amphoteric because it can react with both acid and base. But how that is related to inert pair effect? Okay, so this is not the consequence of inert pair effect. Come to the next one. PbO2 is an oxidant. Now PbO2 means what? Here the oxidation state is 4 plus. Now Pb, when it is in 4 plus state, it is always having a tendency to accept electron and itself be converted to 2 plus, because this state is more stable, and that is because of inert pair effect, right? So that is why this is, here we can say this is the consequence of inert pair effect. And the last one is CCl2 is unstable, but PbCl2 is stable. Now C is here, then you are moving to Si, then there is germanium, then tin, then Pb. So Pb and C is the first element, Pb is the last one. And for C, plus 2 state, this is not possible. And we have already seen that for in the halide slide, remember it is clearly mentioned that for carbon and silicon, halides not possible. Even if it is there, it will be highly unstable. And for even forget about halides, whatever we have discussed. We know that for carbon, 2 plus state stability not possible, because here inert pair effect is not operating. Inert pair effect is operating for lead only. So PbCl2 will be stable because of inert pair effect, not CCl2. So this is also the consequence of inert pair effect. So D and E, the last two, are basically consequence of inert pair effect. So option 2 will be the correct option. Now we will start after this discussion of problems that are mostly related to oxide and halides. We'll start allotropic forms of group 14 element. And when we are talking about allotropic forms, the most important element is carbon, for which allotropes are discussed, will be discussed in detail mostly, especially diamond and graphite. So what is allotropy? Allotropy is the property of some chemical elements when they exhibit 2 or more forms or structure within same physical state. Within same physical state means, just take the example of carbon. It has one very important allotrope, which is diamond, another one is graphite. Now both are solid. That means that physical state is same. There is many other allotropes of carbon also. I'm just taking these 2 examples. Both are solid. That means within same physical state. Though both are solid, but their structure, bonding, it is so different that ultimately their physical properties will be very, very different. So in simple words, it is a structural modification because of different bonding patterns. Bonding pattern is different, structure is modified because of that. And that is the reason ultimately they will have different physical property. That is melting point, density, bond length, hybridization. then refracting property, conductivity property, everything will be different, though chemical properties are same. Fine, because after all it is carbon. There is 4 valence electron, it is 2s2 2p2, then how it will change? But physical properties will be changed. So see, here we have, you can see all the allotropes of carbon simultaneously. And how we are doing the classification. For carbon, the broad classification is some allotropes, they are crystalline in nature, some allotropes are amorphous in nature. Under crystalline nature, we will discuss diamond, graphite, fullerene, and CNT. CNT means carbon nanotube. Fine. And under amorphous, there will be discussion of coke, carbon black, which is also called lamp black, and charcoal. You can also see very small images for all these allotropes of carbon. But we'll go into the details one by one. We'll start with diamond. You can see here the structure, right? And just focus on this part. If I consider this carbon, now don't think that the green ones, this carbon, and this is some other element. Obviously, there is no other element, it is only carbon. So this is as if the central carbon, and surrounding it, there is tetrahedral arrangement, there is 4 other carbon. Okay, so just to make the structure easier, it is drawn in this way. So it is the purest form of carbon. All the allotropes, if you consider, and if it is asked which one is the purest form, then this is the purest form. In carbon, in diamond, hybridization of the carbon atom is sp3, and which is clear from this type of tetrahedral arrangement. It will use 4 sp3 hybridized orbitals for 4 carbon-carbon single bond formation. This is CC bond, CC bond, CC bond, CC. Tetrahedral empowerment. And carbon atom is bonded to 4 neighboring carbon atoms by 4 sigma bonds. So 4 sigma bonds, 4 sp3. You can compare it with methane. In methane, what we know, there is 4 CH bonds, but instead of CH, now we have CC. That is the difference. And this is network structure. Okay. Next, you will see all the bonds in diamonds are of same length, that is 1.54 angstrom. Now, if I give you the data of average CC single bond length, then average CC triple bond and double bond. So the average bond lengths are somewhat like this, that is 1.54 angstrom. For this one, 1.34 angstrom. And this one, 1.20 angstrom. So here, as you can see the value 1.54, that means the bond is CC single bond type, and all the bond lengths, bond angles, is angle if you consider, it is also same. And this tetrahedral arrangement, it is not just fixed at one part, it is extending through entire lattice, right? Now this is 3-dimensional network solid. And because of this type of network, extended network structure, it is the hardest substance known until now. Its high density is very high. I am not saying that density is highest, but because of this network structure, it is the hardest substance. So that is, it is used to cut glass. But its density is very high, and melting point is also very high because of this type of network structure, because you have to break many CC bonds if you want to convert it from solid to liquid. So melting point is high. Melting point is around 4000 degrees centigrade. Now, though it is covalent compound, but still the melting point is very high. This is the unusual combination. Normally, high melting point we observe in case of ionic crystals, where you have to break all the, that is, you have to provide the lattice energy. But here that is not the case. But the structure is so extended and network type of structure, we have to break so many CC bonds. So that is why MP is very high, though it is covalent. So it is because of this strong CC covalent bond which we have to break throughout the entire structure. So that is the reason of its high melting point. This is a bad conductor of electricity. Now to conduct electricity, there must be some free electrons. But as you have seen here, no free electrons are present. It has carbon is used. It has already used all these 4 valence electrons for 4 bond formation with neighboring carbon atoms, and there is no free electron. So how it will be conductor? That is, electricity conduction is not possible. But remember, there is another type of conductivity which is thermal conductivity, and thermal conductivity is possible for carbon. Thermal conductivity, it is basically when we talk about this, though it is very higher level discussion, but if you are interested, I am just saying there is a term which is called phonons. I am not saying it is photons. There is a term which is known as phonon. Now phonon is just like photon, but in photon is when we consider it, it is electromagnetic energy packet. But when I am talking about phonon, it is basically energy packet of vibrational lattice of atom. It is different, and thermal conductivity is directly related to this phonon. And if you, that is the compound for which we are talking about thermal conductivity, if it is having very tight structure, I mean to say, though it is not ionic type of lattice crystal structure, but it is having very highly extended network type of structure. So it is very tight structure, there is no free electron, and because of this tight compact structure, there is few scattering center for the heat vibration. So phonon scattering is basically responsible for heat transfer or heat vibration, which is again related to thermal conductivity. So phonon is energy packet of vibrational lattice of atom. But here, because of this compact structure, the scattering centers are very low or completely absent. So that is why heat vibration, that is for heat vibration, it is helpful. So as there is few scattering center or complete absent of scattering center, so that is why heat vibration is possible. So thermal conductivity is possible. So remember, diamond is very poor. That is, electrical conductivity is not there, but thermal conductivity is very, very good. Okay, it is so good that sometimes it overcomes the thermal conductivity of metals, because we know for metals it is very good, but for diamond, though it is not metal, but its thermal conductivity even sometimes greater than metals. Diamond can reflect and refract light because of its high refractive index. So these are some of the features of diamond, and next when we will discuss graphite, you will also be able to understand the differences between these two forms. Now what about the uses? It is used for cutting glass because we know this is the hardest substance. Then rock drilling, making abrasive. Cut and polished, we know it is used because of its shiny nature, it is used in jewelry. Sharpening hard tools for making dies for drawing thin wires from metals. And manufacture of tungsten filament of electric light bulbs. So after diamond, next we will go to graphite. As you can see, the structure is very interesting. Here we have, just I am numbering it. Suppose this is number 1 layer, this is number 2 layer, this is number 3 layer. So there is so many other layers as you move up and down. And between each layer, there is some blue dotted lines you can see. So these dotted signs, it is basically weak van der Waals force. Okay. And the distance between two layers, that is also mentioned. And these are the CC bonds, that is covalent bond. Now we have seen the purest form for carbon is diamond. But if we talk about the most stable allotropic form of carbon at normal temperature and pressure, then you have to talk about graphite only, not the other allotropes. So that is why in physical chemistry you will see, that is thermodynamics, or equilibrium chapter, whenever we write carbon in solid form, we always take the graphite form, because at normal temperature and pressure, this is the most stable allotropic form. If you look at this graphite, it will look as black, but that is when it is in very dense condition. But if you break it and make it in powder form, then you will be able to see that it is very deep grayish color. Okay, and there is also some metallic luster presence. It is composed of flat two-dimensional sheets of carbon atoms. So these are the sheets number 1, 2, or 3, or layers. Each sheet, if you focus, there is a hexagonal net of sp2 hybridized carbon atoms. Now, unlike a diamond where the hybridization is sp3, now it is sp2. Okay, this is the difference. Now come to the cc bond length. The cc bond length is 1.41. Now remember what I have said, that for cc average bond distance, if you consider, it is 1.54, and for average cc double bond, it is 1.34. But when you have something in between value, that means there is intermediate nature. It is not completely double bond, it is not completely single bond. And that type of bond we see in the benzene, because in benzene this there is delocalization. So at one time this bond is single bond. Then if you consider the another structure, then now it is becoming double bond. So that is why it is having some intermediate bond distance. So in benzene, the cc distance is 1.4. Now look at the value for graphite, it is 1.41. That means you cannot say it is completely single bond or completely double bond. And there is the carbon is sp2 hybridized. It is not like sp3 as we have seen in diamond, and it is planar in nature. It is not tetrahedral. So each carbon, there will be 3 sigma bonds with 3 neighboring carbon atoms. 3 neighboring carbon atoms, as you can see. And what about the 4th electron? sp2 hybridization means what? After hybridization, there will be total 3 sp2, and there will be one orbital which is unhybridized pure p orbital. These 3 are sp2, sp2, sp2. Now this sp2, the 3 electron, that will be used for bond formation with 3 other carbon, and all these are sigma bond. But when there is also one more electron which is in pure p orbital or unhybridized p orbital. So this 4th electron, that will be forming a pi bond, right? And this electron is also comparatively free. That is, compared to the other 3 electrons that are present in sp2 forming 3 sigma bonds, this 4th electron is comparatively free. It is loose. So these pi electrons, it can be delocalized over the entire sheet. And that is why now you can expect electrical conductivity, which we have not seen in case of diamond, right? And also it is having some metallic luster because of this free electron, or not completely free, but it is delocalized over the entire sheet. Okay. Now, as you can see that one sheet, then second sheet, in between these 2 sheets, there is weak van der Waals force. So because of this weak force, one sheet can be easily slipped or glides over the other sheet. So one layer can slip over the other because of this weak force, and the distance is already mentioned. And one interesting consequence that we can write with pencil, it is so soft, right? The graphite is so soft, we can write it so easily. It is because of the slippage of one layer over the other. Fine. So electrical conductivity is good. Thermal conductivity, if you consider compared to diamond, now obviously it is lower, because thermal conductivity will be better when the structure is compact, so that heat vibration can occur easily because of low phonon scattering. So when there is compact structure, tight structure, then only thermal conductivity will be very good. But if there is some loose electron or delocalized electron, obviously compared to diamond, here the structure is not so compact. And thermal conduction is because of transfer of thermal vibration from one point to another point, and that is easier when it is compact crystal structure like diamond. But when it is layered structure of graphite, where the layers can easily slip over other, you cannot say it is compact structure. So thermal conductivity, it is not so good as diamond. Okay. So these are the differences. Hybridization is different. Here it is sp2, there it is sp3. Here we have 3 sigma bond 1 unhybridized p orbital, and that is responsible for electrical conductivity. But in diamond there is no such thing. Thermal conductivity in both cases present, but for diamond it is better. So these are the differences. Now come to the uses. These are very versatile use. It is reducing agent in steel manufacturing. That graphite is ultimately carbon, so it can act as reducing agent. Suppose it can accept oxygen from other species and itself be converted to CO or CO2. As a refractory material for making electrodes for dry cell, we know in lead pencil we call it lead pencil because of this almost black colored. Now if you are asking why it is called lead, it is known in this way. It is not that lead is present, it is simply called in this way as it marks paper black. In the manufacture of crucible, because it can withstand very high temperature, and for making crucible high temperature resistant must be present. As a moderator for fast moving neutrons in atomic reactors, and solid lubricant. Now this is interesting. Normally lubricant we know it is liquid in nature, some oily type of stuff, but in heavy machinery sometimes oil we cannot use for lubrication. In that case we need some solid lubricant. So graphite is that type of lubricant. It can act as lubricant because of this same reason. Again I have to say that one layer can easily slip over the other. So that is why some lubrication is possible, but it is solid lubricant. So diamond and graphite we have finished. Now we will come to the third allotrope of carbon. As we have seen in the first slide, all the allotropes you have seen. Now this is number 3, fullerene. It looks like a ball and it is having large spheroidal molecules. Composition is C2N and it is cage-like structure. That means inside there is some vacancy, right? So fullerene constitute a new family of carbon allotropes consisting of large spheroidal molecules of composition C2N. N is very high value. These were first prepared by evaporation of graphite using a powerful laser. Fine. So it is laser means where you have many photons having same wavelength, very powerful, and when there is evaporation of graphite, this is produced. But it is not just one type, there is so many different types of fullerene, but among so many types we'll keep our discussion mainly on just one type of fullerene. So unlike graphite and diamond, these are discrete molecule. Graphite and diamond, what we have seen, there is some extended type of structure, but in this case that is not so. It is discrete molecule, separate molecules, C32, C50, C60. Now among these we'll focus our discussion on this one, C60. The C60 molecule, it have a molecules basically. There is so many variations maybe there. So these molecules, they will have soccer ball-like structure, and the name is Buckminster fullerene or buckyballs because of its similarity in shape or structure. Now how we can produce this C60? When we heat graphite in an electrical arc, very high temperature, in presence of inert gas atmosphere such as helium or argon, then a sooty material is formed by condensation of Cn small molecules. So at N value it is small, but when they are condensing together, now we are getting C60. The sooty material so formed, it mainly consists of C60 fullerene, though there may be some small amount of C70 also, and traces of other fullerenes, because we have seen here different types of fullerenes are there. So some other fullerenes consisting of even number of carbon atoms, but that is not greater than 350. It is either equal to 350 or up to 350. Fine. So it will be less than sign, not up to 350 means either equal to or less than. Next, we will see some more information related to this. Now look at this structure very carefully. Here This is 5-membered, right? Now just look at the surrounding of this 5-membered ring. You will be able to see this is a 6-membered. This is another 6-membered. 6, 6, 5, 6, 6, 6. So surrounding this 5-membered ring, there is total 5 6-membered ring, right? And that means surrounding 5, there is no 5-membered ring. This is a very important feature. But surrounding 5 members, there is only 6-membered ring. And what about the 6-membered ring? So see, this is one 6-membered ring, right? And surrounding it, there is 1 6, there is 5 also. So surrounding 6-member, there may be 5 6 both, but when it is 5 at the center, surrounding it only 6-membered rings are there. But how many? It has a fused ring structure consisting of 26-membered rings, 12 5-membered rings. This is important information. Okay. Here also carbon is sp2 hybridized because you can see there is both. That is, if you consider a single carbon surrounding this, there is 3 sigma bonds, 1 pi. So it must be sp2 hybridized. There you can find some similarity with graphite. So 3 sigma bond, 1 delocalized pi bond, which is not part of hybridization. Pure p orbital. There will be a electron which is responsible for pi bond. Then there will be some aromatic type of character, just like benzene. Now the C60 fullerene, there is total 60 vertices, and each of these vertices is occupied by one carbon atom, and this one carbon atom contains both single and double bond. So just consider any one carbon. So there is both single bond surrounding it, and there is also double bond. Okay. CC bond distance is 1.44 angstrom if you consider the single bond, and CC double bond is 1.38. It is lesser than this, obviously. Fullerenes are the only pure form of carbon because they have smooth structure without having dangling bonds. Dangling bonds means here you will not find any extra electrons which is free and which can form one more electron. So there is some smooth structure. Dangling bonds are not present. That is, extra bond formation tendency is not present, which can attract other atoms, as in case of graphite or diamonds. In case of graphite, the delocalized electron, it can form another bond with another atom. And in case of diamond, though it is compact structure, but if you remember the structure of diamond, just the structure consider that I have used. Just consider in the corner position where, that is, I'm talking about, just look at the structure of diamond. If you look at the corner position, that is, I'm talking about this one, then you can find some dangling bond. So it can again react with some other atoms. So this type of tendency is not present in fullerene, and that is the difference with graphite or diamond. So that is mentioned here. So this compound, one more information, when doped with alkali metals, they behave as superconductor below 18 Kelvin. Superconductor means zero resistance, but that is possible when it is doped with, that is, some impurity of alkali metals are added, then only it can act as superconductor, but below 18 Kelvin. Fine. So in the next class, its use and also the other allotropes will be discussed. We are ending the session here. Thank you for listening.